Hey guys, Professor Doney back. We're still talking about projectile motion, or two-dimensional motion, meaning it projects or lands somewhere else. We're going to do a problem here of driving off a ramp and launch. It's going to have the same launch and landing heights. So it's going to go from ramp to ramp, essentially, same height to same height. And let's just give us some numbers here. Let's say our angle is 30 degrees, just for something easy. Let's say our initial velocity off the ramp is, I don't know, just 10 meters per second. Alright, no big numbers, don't need to. Okay, so we have a ramp here. We're going to draw a little car. And there's the velocity it's going to go off for, and because of gravity it'll go up and then it'll come back down, and we're just going to assume it lands on an identical ramp on the other side. That way it's the same launch height as landing height. Okay, and what we want to find out from this is a couple things. Let's find out how far away the object lands. So a different color here, which is going to be this. Since that's horizontal, we'll call that delta x. And we could also find its maximum height, which is just y max or y up. That could be the peak, meaning how high does this thing go as it goes across the ramp. And that's important if you're trying to jump over something, obviously. Now, a couple ways we can solve this problem. But first off, let's put down some, we need to pick our coordinate system. We typically have x to the right, positive y up. And the one little trick here with projectile motion problems is that since this is at 30 degrees to the x, it doesn't line up with x or y, so we always have to deal with this. And Galileo, I believe, was the one that said we have to break it into components. So we're going to treat that 10 meters per second at 30 degrees like a right triangle, that side being 10, here the angle of 30. We're going to find the x and y here. So to find the x, we have to find 10 cosine of the angle, which is 30. That should come out to be 8.6 if you're using your calculator in degrees, which you need to be. And the y will be sine of 30, because this is the side opposite from the angle. And that should give you a 5, which is up. Okay, so how do we solve this? Well, once we start with this, we only use this velocity in the x and this one in the y. We no longer go back to the 10. Now, a couple shortcuts you can go with here. Typically, we don't like to use this equation, or I personally don't, just because you have the possibility of ending up with a quadratic equation, a t squared plus something t plus something equals 0. But since we're going from the same height to same height, our vertical distance is really 0 at the end of the problem. So if I make that 0, my initial velocity 5, because that's upwards, right? We're going positive up. And that's 1/2. It's minus 9.8 because gravity's down, and that's t squared. We rearrange this, we get a 4.9 t squared minus 5t equals 0. Now, it's sort of a quadratic, but it's missing that third term, the t squared minus 5t plus. There's nothing else here. So this easily factors into t times 4.9 minus, sorry, I had that backwards. 4.9t minus 5 equals 0. Now, for this to equal 0, either t equals 0 or 4.9t minus 5 equals 0. Now, this corresponds to, this first t corresponds to when the problem just starts. Yes, it's at its lowest point when the problem starts, so that's correct. For this one, if we solve for, set this equal to 0 and solve, we'll get 5 over 4.9, which is pretty much 1 second. That's our second answer, or second root. When we have a t squared, there's always 2. So what we find out is we're in the air for 1 second. We can move to our x equation too quickly because I'm running out of time. Put in here, we use our horizontal 8.6 times 1 second. That tells us we land roughly 8.6 meters away from where we started. Now, I didn't get to the max height. We'll come back and finish that up here in the following video. So I hope that helps for a same to same. You can set and use this equation, which I typically do not use because of the t squared, but when it's 0 height, it works out. So hope that helps. We'll see you next video. Okay guys, Professor Doney here. We are in the middle of solving a ramp-to-ramp projectile motion problem where we have the same launch and landing heights. So we're going from same one ramp to an identical ramp later. Alright, to keep it easy. And we went through and found out the components of that velocity at 30 degrees. 10 at 30 degrees is the same as 8.6 horizontal and 5 up at the same time. This is using the sine and cosine with the hypotenuse, and we're told to do that through Galileo to break it into components. And we went through a solution. We found out the time in the air was about 1 second. Okay, we're going to go through another solution. The way I like to do it is break it up, use some symmetry, worry about the up part, and since it's identical on the way down, we can double that. And what we're going to treat it as is a throw-up problem. As I like to tell my students, let me change that color, it's not too great. And the way we're going to do a throw-up problem, use our y equations. We know when we throw an object up, it'll keep going up until its final velocity goes to 0. It goes to 0 at its peak. So v goes to 0 at the peak. And that's sort of the boundary or the key to doing vertical motion problems when we throw them up. So we're going to make that final velocity 0. Initial is 5. Why do we use 5? Because that's in the y direction. We're going up. That's a throw up part. Plus minus 9.8 y minus, because we're throwing it up as positive. Gravity is against that, so it's negative. We go through here. T will equal minus 5 over minus 9.8, and that comes out pretty much to be 0.5 seconds. Now you should know when you're going through these problems, it's rare that you're going to get a negative time. And I like to tell my students that if you get negative time, it implies you went back in time, and they don't know enough right now in the course to do that, so they should check their signs. Chances that I missed the sign. So that tells us it takes a 0.5 seconds to go up. So if our t up is 5.5 seconds, it has to equal our t back down. Why? Because if we go up a certain distance, we're going to come back down that same distance since we are at the same launch and landing heights. That's the key to go back there. So that makes our total air time 1 second, and I can put that into our horizontal equation, which we have, and that'll tell me my initial velocity horizontally is 8.6. That comes from doing the cosine times that 1 second, and it does confirm from our previous problem that we're about 8.6 meters away. So that's a different way of doing it. A little more tedious, maybe an extra step than using the delta y equation, but just as valid, I think cleaner, unless you recognize the same height, same thing. Now what I also want to find out is the max height that this object reaches. And I'm still trying to find colors that seem to work well, so I'd certainly take your input. If you say, hey, this color doesn't work, let me know. I'm working on my handwriting, but what I got is what I got. So max height, we're still going to do a throw up problem, and what we're going to use is the final velocity goes to 0, and what we'll do is go to that second equation where it's v squared equals vo squared plus 2g delta y, because that has distance and it has our initial final velocity. So we're going to use that. We're calling positive up still. Final velocity 0 squared. Initial velocity 5 squared. Again, we go back to using our vertical velocity. Plus a 2 minus a 9.8 because gravity is down against our positive up. Delta y. We find out the delta y is going to be, what does that come out to be? Minus 25 over minus 19.6. That gives us 2-ish meters, doing it off the top of my head. It's about a 4-foot person kind of thing. So it's not a huge jump in today's terms if you look on YouTube and see what some of these guys and girls are doing on bikes and four-wheelers and sleds. But it does allow us to find out where to put the ramp to land or how far away it lands, and that is going to work for any object in the absence of air resistance to make it easier. Whether we're using a car here, or we're doing our bike or a four-wheeler, or we're shooting a gun or a potato gun or a slingshot or throwing a javelin, this is going to come up with the same solution. So hope that helps, and we'll check you next video.